Good morning. We are ready now to move on into Chapter 3. So we took a good thorough look at Chapter 2 and looked at all the details with displacement and velocities and accelerations, calculating those for different types of motion in one dimension. And now what we're ready to do is move on to kinematics. Again, that kinematics, it's going to impress your friends. 2 or 3 dimensions. Now to do this, we use a mathematical technique called vectors. Now some of you may have already studied vectors in Calculus 3, is that where it comes up? This may be one of those examples where we see something first in the physics class and then you'll see it later in your math class, but it's a pretty straightforward approach to what we've already done. Here's a list of all the topics. I'm going to move past those. You guys can use those if as needed, as you want. So what it's saying is that the quantities, we're going to actually start off with vectors as a discussion point. Physical quantities come in a couple different varieties. In physics, we have quantities that are classified as scalars, and we have quantities that are classified as vectors. Scalars are quantities that just have one number associated with them. So some good examples of scalars are things like mass. You know, when I measure the mass of an object, that's its mass. It doesn't require any more information. We've told the whole story about mass with that one number. But we have other quantities in physics that fall into the category of vectors. Now, our space is three-dimensional. We use three-dimensional coordinate systems x, y, and z to keep track of locations in space. Many of the physical quantities we work with have 3 separate, what we call components. Velocity, for example, we could have a velocity that's going exclusively in the x direction. We could turn and have a velocity go in the y direction, and turn and have a velocity go in the z. Or we could pick something in between. We could pick something intermediate. We could have a velocity heading off at some angle. How am I going to represent all the different ways that velocities could be headed? And it turns out we need 3 numbers for that. We need what we call the velocity in the x direction, velocity in the y, and the velocity in z. So if I'm going exclusively in the x direction, all I have is a velocity in the x direction. But what if I'm going kind of diagonal? Well, if I'm going diagonally, I can think of that diagonal velocity as having an x contribution or component and a y contribution or component. So velocities, and I guess that's what they've got going on with this car, velocities are three-dimensional and they fall into the category of vector. Now displacements are vectors also. So when we look at displacements could have an x contribution, a y contribution, and a z contribution. Velocities are three-dimensional. What about accelerations? Well, yeah, the accelerations would have to be vectors also. So what we're going to find is, as we go through all of physics, everything either falls into the category of a scalar, which is just one number, that's an easy thing to work with, or what we call vectors that have these 3 spatial components to them, x, y, and z. So some other vector quantities, let's see if we got them all. Displacement, velocity, acceleration. We haven't looked at forces yet, but when we apply a force on something, when we push on something, there's actually 3 different directions we could, the push that we do could have 3 separate components to it in the x, y, and z directions. So forces are vectors also. It turns out this thing called momentum that we'll explore. So vectors have, there's a couple ways of looking at this. Vectors have what we call magnitude and direction. So if I'm traveling with a certain velocity, there's a couple different ways I could report this. I could say I'm going this fast and I'm going in this direction. And directional information is usually given in terms of an angle. So let's take a look at the examples here. The other alternative would be to be reporting X, Y, and Z directions. So here we go. If we have motion in one dimension, even for vectors, as long as we stick with one dimension, we can just add and subtract. So if I traveled 8 kilometers in the east direction and then 6 additional kilometers in the east direction, that's 14 kilometers east. That wasn't too difficult to add those two displacements together. If I traveled 8 kilometers in the east, or positive x direction, the way we've designated this, and then I came back 6 kilometers, well, that would be 8 minus 6. That would be 2 kilometers. So we have to be careful about adding or subtracting, but these two vectors, which I'm representing with arrows, we could add those together, or we could subtract them by lining them up this way. Now, if I want to do an addition, there's a couple different ways we can do addition of vector quantities. Displacements, it's handy to just take one displacement and then just pick up wherever we left off. That works. So we can go from tail to head, and then pick up with the next vector and set it next to the head of the last vector, and then add it in. So that provides a nice graphical method for us to keep track of, and what we're looking at here are displacement vectors. Now it's still only one-dimensional, even though they're vector quantities. Aha, here's where we're now finally going to be two-dimensional. Let's say that, and for some reason they're using capital D here for displacement, so that's fine, I'll go along with that. So let's say that instead we go 10 kilometers in the east, or the positive x direction is what we're designating that as. And then what we do is we have 2, 4, 6, 8, 1, 2, 3, 4, I guess it's 5, huh? Yeah, 5 in the north, or the y direction is what they're calling it. And so that's 10 kilometers this way and 5 here. Now where that leaves us is at that point right there. So it's got an x component to it, and it's got a y component now for the displacement. The x is equal to 10, and the y is equal to 5. Well, how far are we from the starting point? So from where we started, we can find out how far we are away from that. That would be displacement. These two individual displacements have led to what we call a resultant displacement. So the resultant displacement for this, because I have x and y portions, I can use Pythagorean's theorem. So that's going to be key for us. If I can make sure that the components, the individual displacements, are represented perpendicularly, then I can always come back and use Pythagorean's theorem to figure out what the total displacement is. Now, we said to represent this vector, we could do this. We could just state that the vector consists of x equals 10 and y equals 5. That would do it. That's called component form. So if all I do is just take the total amount in the x and the total amount in the y and state those, that's reporting the components of the displacement. Now the other way would be able to come up with the magnitude by calculating this diagonal value. Now that's not enough to designate where we're located, because once I've calculated this distance, I still have to know what the angle is. If somebody tells me this distance, I'm starting at the origin, and someone says, look, go this far away from the origin, that's not enough to designate where I need to end up. I would also need an angle. So if someone tells me the total displacement and the angle, that's enough information to identify that point. Or, alternatively, if someone says, go x for 10 kilometers and go y for 5 kilometers, that works also. So two different approaches two different sets of information that we could work from. Now, notice that the displacements that we talked about, displacement 1 was here and then displacement 2, if I reverse the order of my vectors, it doesn't change anything. If I now do displacement 2 first, and then I do displacement 1, it still leads me to the same location. Okay, and that's whether they're perpendicular or not. So vectors can be added together in any order. Does not have to be in a particular direction. Now here's a bunch of vectors. They're not at right angles anymore. Let's say that we have a vector v1 here. I don't know if the v's are vectors, if they represent displacements, they could be velocities, accelerations, but if we take this much v1, let's say it's a displacement, and then we follow it up with this displacement, and then we follow it up with this one, what I can do then is I can take this vector, I can start out a vector diagram by saying I started right here, and then I traveled this far, and then my second vector says I traveled this far in this direction, and my third vector says I traveled this far in this direction. However far we are from the starting point would tell us what the total displacement or the resultant displacement would be for that. And so that's a vector diagram adding all of these together. Now that's a useful approach, but we're going to find out that there's probably a more useful systematic way of adding vectors together. But this certainly works. So just graphically adding them tail to tip definitely works in combining vectors. Now, these don't have to be displacements. If it were just displacements, that would be kind of a useful approach. But these vectors could represent, let's say they represent forces pushing on something. So if I had a force pulling something off in this direction, and then I had something pulling it down here, and I had something pulling it here, what would be the net effect of all of those forces? And the resultant that we've calculated would be the net effect. We'll see more examples of this. So when I'm adding vectors together, here's something we really have to be careful about. Here is vector 1, here is vector 2, and we've looked at a couple of ways of doing this. We said that I could start with vector 1 and then add vector 2 onto the end of vector 1, and that would give me my resultant. We could also start with vector 2 and then add on vector 1. That would give us a resultant. Those are like parallelograms once we've drawn all those in. We can also do this. We could say, well, v1 could represent a certain amount of something in this direction, and v2 is representing maybe these are forces again. So here's a force in this direction, here's a force here. If we pull this much in this direction and this much in this direction, the net effect, the resultant, is going to come from measuring the parallelogram. Now that last diagram shows that there's a way to confuse ourselves. So that's the one we've got to be really careful about. If I take V1 and V2 and add them together, V1 and V2 added together don't represent the difference. This is the difference between them, not the addition. So this would be V1 or V2 minus V1. Is that right? So be very careful with this addition versus accidentally subtracting off a vector. Okay, we can put coefficients out in front of vectors. So if this is vector v, then negative vector v goes in exactly the opposite direction. So I could take v2, I could subtract off v1. That would be the same thing as taking v2 and adding the reverse of vector 1. So I could use that approach to get a resultant. Okay, we can multiply by numbers, by scalar values. What we can do is take a vector, let's multiply it by 1.5 to get a different vector. Let's multiply it by -2 to get a different vector. So we can, these are scalable. So I can make the vectors bigger or smaller multiplying by coefficients. Now here's the approach that we're actually going to make a lot of use of, and that is adding vectors together by components. So what we can do is say this. Let's say that we have a vector and it's oriented at some angle. Well, it's going to have an x component and it's going to have a y component. And the way we can identify graphically how large those components are is we can draw a rectangle. We can draw a rectangular box around the vector from tail to tip. And then the components will be represented by the sides of that rectangle. So the sides of the rectangle are equal to the components of the vector. Now I wrote down here a note that more generally it's going to be three-dimensional, not very much in this class. So we're going to save a lot of the three-dimensional stuff for, if you're engineers, you'll see this in taking statics. So when you're looking at forces acting on things, you'll have a lot of three-dimensional examples. For us, we're just starting out, and so 2 dimensions for the most part. Occasionally there will be a 3-dimensional problem thrown in into the homework, but in general we limit ourselves to looking at 2 dimensions. Okay, so here we are taking a look at that diagram again. Now, I'm calling this Vx and I'm calling this Vy. So this side is Vx and this is Vy. Well, you know, this is going to also be Vy, so I could measure Vy here or here. I prefer, for the most part, I prefer working from the approach where we put both components coming out of the origin, but you can also do this tip-to-tail approach. That will work also. So these 2 sides of my rectangle are the same size. They're both Vx components. These 2 sides are both Vy components, and then the vector itself runs diagonally. Now what we can do is we can dredge up some trigonometry and go, oh yeah, I remember trigonometry. So the sine of theta, let's designate an angle. The sine of theta would be opposite over hypotenuse. That would be Vy over V. Cosine of that angle would be Vx over V. It would be adjacent over hypotenuse. Tangent would be Vy opposite over Vx adjacent. And then Pythagorean's theorem gets thrown in. So this is how we work back and forth between representing a vector in components versus representing a vector in terms of what we call a magnitude. So the magnitude of this vector is V, and that's the distance from tail to tip of the vector itself. The Vx are the x and y components, or the x and y projections, projections of the vector onto the x and y axes. So if components are perpendicular, then we can use, and they are, so when we're working in component form, they are perpendicular. So we should be saying the components are perpendicular, and we can designate them using these functions. Now, what if instead of using this angle, what if we used this one? This angle right here, see that? If this is theta, well, this is theta's complement. Now, if I choose to use complement of theta, if I choose to use the other angle instead, what that would do is it would, the sine of theta is the same thing as the cosine of its complement. The cosine of theta is equal to the sine of its complement. So the sine and cosine would switch. Those formulas would change if we use the angle over here. So the thing to remember here is the cosine component is the one that's adjacent to the angle. Cosine is adjacent, sine is opposite. So if I take a look at this angle right here, this side is adjacent, this side is opposite. So again, the angle, here's the hypotenuse. If the angle is in here, that's the adjacent component. This is the opposite one, which matches this is the opposite one too. If this is how I'm designating my angle, then this would be adjacent. It would pick up a cosine factor. And this side, so the sides, the adjacent and opposite would flip. Okay. Something to keep track of. Ooh, so here's how vector addition in general will work using components. Let's go back and look at that example where I had v1, there's a vector, and then here's another vector, v2, and then we combine those into the resultant. Well, what we could do is we could take v1 and divide up into x and y components. Then we could take v2 and divide that up into x and y components. If I look at the overall x component for the resultant, it's going to be the combination of v1x and v2x. So I can add together all of the x components. In this case, there's just two. I can add the x component from vector 1 and the x component from vector 2 to get the overall x component for the overall vector. I can do the same thing in the y direction. Vector 1 took me from here to here in the y direction, and vector 2 took me from here to here. I can add v1y and v2y. I can add those two y components together. Those are going to give me the total vy. So that's the way this typically is going to work, and we will see a lot of examples. Draw a diagram, adding vectors. We're not going to be adding them graphically very often. That is always an option that's out there. But so draw a diagram. Let's draw the vectors graphically. So more often than not, we'll draw the vectors that we're dealing with. And then we will resolve them, is what it's called, into components. And then we'll combine the components using the sine and cosine formulas. And then we can find the magnitudes and the angle using Pythagorean's theorem and using trigonometric definitions. Okay. Now I hope we haven't frightened everybody by all this discussion of vectors. We're going to get back to motion here in just a little bit. So here's a mail carrier, and they traveled north for a certain distance, and then they traveled kind of southeast for a while. It's going through and showing how to combine these together. So let's take a look at these. What I'm going to do is I'm going to write it as there's a vector, there's a displacement vector that we started with. I'm not going to do this tail to tip stuff. What I'm going to do is say this displacement was followed by this displacement. Where is that going to lead us to in terms of displacement? The first vector, d1, oh, that's d2. I didn't get that added in. That's got to have a 2 on it. So this is d1. It consists of components x1 and y1. X1 is 0. If I look at that first displacement, it's not going in the x direction at all. And so I can just write that as 0. And then it's 22 kilometers, really. So this mail carrier is in a vehicle, right? Oh yeah, she's driving. Okay, I was thinking it was... Okay. So there's a long ways to walk. But you got to get the mail through, whether storm or rain or whatever. So 0 and 22 kilometers are the components for that. And then what happens is, she turns the vehicle and then travels diagonally. Now I got to find out for displacement 2, how much x am I getting and how much y am I getting? And so we can use our cosine formulas. So it said 47 kilometers at an angle of 60 degrees. So that's going to give us values of x2 and y2 that are 23.5 and 40.7. So those are the numbers that I ended up calculating for that second displacement. Then to get the overall displacement, to add these vectors together, we line things up and say that the total x is x1 plus x2, which we're now going to call x, which is 0 plus 23.5. So when I combine all of the x displacement that has happened, I've got a total of 23.5. Now in the y direction, the first displacement gave us 22 kilometers of displacement in the y. For the second displacement, I'm getting 40.7. Okay, so when I add those together, and that's in the opposite direction, I get negative 18.7 kilometers. So that's going to end up leaving us, well, down here. So let's now say that the overall effect in the x direction was 23.5 kilometers, and the overall effect in the y direction was negative 18.7. So compared with where this person started out, so let's see, they went north for a ways, and then they went at 60 degrees. It's going to bring them to that point, and so the total displacement can be calculated using Pythagorean's theorem. We'll take the total dx and square it, the total dy and square it, take a square root. It says, as a combined effect, we're 30 kilometers from where we started. Now we can also calculate an angle by taking dx and dy and dividing by dx. Now I put absolute value signs on this because we typically move from quadrant to quadrant. This might be designated as a negative angle, but I'm not really interested. I can see from the diagram how it's oriented. I just want to find how large the angle is. So rather than designate that as a negative angle, what we can do is just take absolute values and take the inverse tangent. So rather than trying to keep track of plus and minus signs within the trig functions themselves, which is doable, if you prefer that, that works. It's, for most people, I think it's easier to work within a quadrant at a time. If I'm working within one quadrant, then these angles are all going to come out between 0 and 90. And if I'm working between 0 and 90, then the cosine and sines are going to be positive throughout that region. So I don't, so what I ended up with was that the angle is 38.5 degrees. Okay, so that's an example of combining those vectors. Okay, so it says we're going to take 3 short trips. We're going to do one more example of this, I guess. So the 3 short trips we're taking, oh, it's an airplane this time. So we're traveling this far directly in the x direction, and then we're going to turn, and we're going to travel this far. They got to give us the numbers. Okay, the first section, first leg, is 620 kilometers. The next one is 440 at a 45-degree angle. And the third is 550 kilometers at a 53-degree angle defined here. So see how we're doing this as quadrants. This is 45, and then this is 53 here. So they put together a nice table. So let me just step aside here. And so for each vector, they've listed how much of that vector is in the x direction and how much of the vector is in the y. So what are the components? And for the first one was easy because it was exclusively in the x direction. So 620 in the x kilometers, nothing in the y. The next one was at 45 degrees. Now, I'm going to have to use sines and cosines to calculate that. So sines and cosines of 45 are going to give me the same number, and then I multiply that by the 440, and that gave me 311 in the x and 311 in the negative y. So here I do have to keep track of plus and minus signs in my x and y directions. And then finally the last displacement was taking me negatively in the x and negatively in the y. And I've got to get my calculator out again and take some cosines and sines of 53 to find these components. And then I can add up all the x's, which say that after those 3 separate plane trips, I have moved a total of 600 kilometers in the x direction, and then I have moved a total of 750 kilometers in the negative y direction. So those are adding those individual components together. So here we go. So same problem. I'm going to fill in some of the details here. So I wrote the individual displacements as r. It's very common. We're going to be using r as a distance quite a bit in different situations. So we might as well start. Now I know there's an issue with r. R a lot of times is thought of as radius, but r more generally is often used as a distance. So I just thought this would be a good chance to start using that. So for each one of these vectors, we had defined an r value and a theta. Now, for the thetas to work, I actually had to draw a diagram and show where the theta was that I was talking about. Theta 2 is right here at 45. Theta 3 is right here, and that's 53, and those are left as positive quantities. Now, to find out the components then for vector number 1, I'm going to take the amount, the magnitude, which is 620, multiplied by the cosine of 0 for the x direction, and then r1 times the sine of 0, which is 0, for the y direction. That gives me components. Now that's 0 degrees. Let's look at something non-zero. What happens when we turn and go at a 45-degree angle? Well, if I turn and go at a 45-degree angle, then I want to take the 440 kilometers multiplied by the cosine of theta 2, and then the sine of theta 2 for the y direction. And then I put the minus sign in by hand because I'm looking at my diagram. So I'm using my diagram as a way to determine where to put plus or minus signs. For displacement 3, displacement 3 is in this direction, and I have to know that for that direction, that's going to put me in the negative x direction. It's going to give me a negative x contribution, and it's going to give me a negative y contribution to the overall distances. So that's what's happening with those. Now I took these formulas, the r's and the cosines and the sines, and plugged those numbers in, and that's where their numbers are coming from. Okay, so if you look at the chart before, you can see those are the numbers that they came up with. Now, what we would also like to do in a problem like this is say, okay, fine, after traveling these three, I transferred in Denver and I transferred in Atlanta or something, where am I now compared with where I started out, and why didn't I just take a direct flight? Because I'm visiting way too many airports along the way. So let's find out how far we are from where we started. Let's see, what's the total distance that we traveled? So I'm going to get, travel miles, extra something for travel, I don't know, traveling incentives. Let's see, we traveled 620, 440, that's 1,060. This is 1560, 1610. Oh yeah, there I actually calculated it. So we've traveled a total distance of 1610 kilometers, but how far are we from where we started off? And to find out where we started, how far we are, we can take the 600, our total x components all packed together, our total y components, and use Pythagorean's theorem. So Pythagorean's theorem will allow us to show that we're actually only 960 kilometers from home, right? Even though we had to fly 1,610 kilometers to get here, we're not as far away as we might have thought. And then the other item, I designated this as angle phi. So I wanted to find out, in angular terms, in terms of a direction, where are we located? And we are located at an angle of 51.3 degrees relative to the x direction in that towards this direction. So if we're using north, south, east, west kind of stuff, this would be 51.3 degrees south of east is where we've ended up. Okay, so that's pretty thorough. Now, the advantage of the component method is it's very systematic. Whatever gets thrown your way, pretty much, if you can get the individual magnitudes written down and the individual angles, and set up a table like this, and then you just add everything together. If you're very systematic and make sure that you're keeping all the correct values everywhere, it works. Okay, and conceptually, it's a pretty good way to think about the problem solving itself too. All right, now in addition to the vectors that we've talked about, we are going to be making use of what we call unit vectors. Unit vectors, the unit here, means that they have a magnitude of 1. And you're thinking, what are we doing? Why are we introducing this idea of unit vectors? Well, unit vectors provide us an easy way to write down in vector notation how to designate the components. So let's say that we have some kind of a vector, and it has a certain value in the x and the y and the z directions. What we define are unit vectors, and the unit vectors are called, for better or worse, I, j, and k. So, and you're welcome to use the I, j, k notation. I will use it occasionally. I tend more often to use e sub x, e sub y, e sub z with little hats. I didn't get the hats drawn in. So either of these work. I think the IJK stuff is pretty common in engineering. So I think in engineering you'll see a lot of that. When you get into kind of your advanced math classes, and maybe they tend to switch over from IJK and use these little e's. Now I know we use little e's for other things like e, the fundamental number e, but these also get used for unit vectors. So what does that allow us to do? So now we can say that a vector consists of an x component in the I direction, which is the x direction, a y component in the j direction, which is the y direction, and a z component in the k. So they just picked ijk. They could have done x, y, z instead. The ijk works pretty well because the subscripts don't get mixed up with the other subscripts, I guess. The ij and k is a nice way to avoid having to put subscripts on the unit vectors. Now, what does a unit vector do for us? Unit vectors are great because, they're not going to do much more, are they? So unit vectors are great because what that represents is purely direction. So the Vx tells me how much component I have, and the I hat, the unit vector, is purely a direction. So take Vx and place it along the x direction. Take Vy and place it along the y direction. Take Vz and place it along the k direction. Okay, let's do some kinematics using our newfound vectors. So if we're working, these diagrams, I always feel like they're kind of backwards. They start out more complicated, and then they go back and look at simpler examples. But let's do this. This is a very general sort of thing. So here is a path that some object is taking. And notice now it's not a straight line anymore, right? We're not in Kansas anymore. So it's not a straight line. It's curving. And so we have to be able to take, the velocity would be tangent to this path. And so the velocity just keeps changing directions. It's going to have x and y components. Now, if at one time my displacement could be represented by that displacement vector, and later on it's represented by this displacement vector, then delta displacement is written as the vector that takes us from point 1 to point 2. Now, if that required a certain amount of time, we could imagine doing an average velocity. We could take the displacement, divide through by the time, and come up with an average velocity. Now, what they're calling the delta L is, I guess, is the actual distance that was traveled. And we can see that the displacement isn't representing that right now. So what we can do is we can take, you guessed it, shorter and shorter time periods. So rather than averaging between here and here, what we can do is we can bring points 1 and 2 close together, and what this represents now is a really short time period in the limit where we bring those two things together. We're going to have what we call the vector, or the velocity vector. This is now velocity. As delta t and delta r, that needs a vector sign on it, become smaller and smaller, the average velocity approaches the instantaneous in the limit. That turns into a derivative. Now you're wondering, how do I take a derivative of a vector? It's got all these components going on inside. And we'll get to that here. So here is how taking derivatives, so this is just for convenience. So we say that the velocity vector is the time derivative of the displacement vector. The displacement vector breaks down into a certain amount of dx, a certain amount of dy, and a certain amount of dz. So a displacement vector will always have those three components. And so what we can do is, that's vx, and that is vy, and that is vz. So more often than not, we're not working in full-blown vector notation. We're usually working in terms of components, okay, is the way this is going to work. And then acceleration works the same way. We take the velocities, vx is defined here, vy and vz, and we take another time derivative to get the accelerations. Now I skipped one of the, no I didn't. Oh, they kind of had 2 pages showing the same thing. Okay. Oh, I see. This is important. So notice what would happen if I picked a different coordinate system. Well, a different coordinate system, then R1 vector would be different, and R2 vector would be different. I got to go back one. But delta R would not. So that's kind of interesting. If I decided the origin of my coordinate system was here instead of here, then R1 would be here and R2 would be here. But the delta R's would not be affected. The delta R's would still represent the path, the trajectory that the object is following. Okay, so it doesn't matter where we define the coordinate system. Now to get the velocity, we said that we take shorter and shorter time periods, and as we get shorter and shorter time periods, the velocity direction becomes tangent to that path. So that's going to become tangent to the path for a particular time. Now notice the graphs we're looking at now are XY graphs. They don't explicitly show time. And so what we know is this. We know that time is increasing as we move along the path. But since we don't know what the velocities are, we don't know how to put in the time information. So we don't know the details of that from the graph itself. Someone would have to supply that. Again, the graph is only keeping track of x and y information for us. Now, if I look at these 2 points, velocity 1 was at this angle, velocity when we were at point 1, and then velocity 2, when we get to this point, is tangent over here, or is it? I don't think they quite got that. Anyway, these 2 lines are tangent. To find delta v, what we can do is we can take the final velocity direction and subtract this off. And you might be thinking, well, I can't bring those 2 vectors together. They're away from each other, but you can. So vectors you can pick up and move anywhere you want as long as you maintain their magnitude. You can't change their magnitude, and you can't change their orientation. But you can lift them up and move them around, and what we can do is say that this vector, vector 2, is represented here. This vector, vector 1, is represented here. Delta v would take us from where v1 left us to where v2 leaves us. So the delta vector needs to be v2 minus v1. If, let me state that another way. If I've already have vector 1, which takes me from here to here, now these are representing velocities. If I start with vector 1, and then I add on a delta v, that will take me to where vector 2 is. So the delta vectors take us from one velocity to the next. Now what that's saying is that delta v's could be in any direction. Delta v's are not necessarily in the direction of v1 or v2. They're going to be in their own direction once we do these diagrams. The delta v vectors are going to be in whatever direction they are. So we looked at this. Let me move on. Okay, so we did kind of, the mathematical formalism of everything going on. And if that works, that's great. And if it's a little confusing, I don't think that's a problem. Let's get down to some practical examples of how we actually end up making use of what we've just introduced. So let's do this. Let's take this vector stuff that we talked about and apply it to constant acceleration. But this time, instead of the acceleration and the velocities and the displacements being exclusively in the x direction, let's allow for them to have x and y components. What is going to happen? And what's going to happen is we're going to take those three equations that we had for constant acceleration, which looked like this, and we can copy and paste over into the y column. So that now, the formulas that we did before, are a set of complete formulas describing constant acceleration in one dimension. In order to get constant acceleration in 2 dimensions, we take the very same formulas, we take out all the x's, and we put in y's. Now, another complication here, I guess, that we have to talk about. Before, we didn't call this ax, we just called it acceleration, because there weren't components. So where there used to be a's and v's, those now have subscripts of x. So now, the vx is looking exclusively at velocity components in the x direction. X is looking at displacements in the x. Vx is looking at x components. These are looking at y components. Now, in general, I could have, if I've got constant acceleration going on, I could have a constant acceleration in the x, and I could have a constant acceleration in the y. But I don't necessarily always have that. So it could be that maybe I have acceleration going on in the x direction, but in the y direction I have constant velocity. So we can apply whichever set of constant acceleration formulas we have for whatever situation we find ourselves in. Okay. So with that said, let's get a start. Let's move on and take a look at what we consider to be projectile motion. Now what they've done here is this. So they've taken this object, and did they say what it is? It bounces pretty well. So we've got this object that bounces pretty well, and it's in free fall. So what we're saying is it's under the influence of Earth's gravity, and its path now is going to be a parabola. Now that's not the same parabola we saw before. Back in chapter 2, when we looked at parabolas, we were looking at x versus t, or y versus t. We were looking at displacements as a function of time. The parabolas they're talking about now is time is being represented now by a series of snapshots. So this is the starting time. This is, I don't know how frequently, let's say this is 1/10 of a second, this is 2/10 later, 3 seconds. So time is increasing as we look at one snapshot to the next. And what's really being graphed out here is y as a function of x. So it's traveling in the x direction as well as traveling in the y direction. So the velocities that we have here are going to be along the path that we see, It bounces here, and abruptly the velocity changes direction. Again, it bounces here and abruptly changes. Now, in between the impact, where it's bouncing, that's what we consider to be projectile motion. So we're only going to consider gravity. So we're just going to look at gravitation again. We're going to ignore air resistance, which means we need an object that's fairly dense and it's pretty good size so that air resistance becomes a negligible effect. But if we do that, and we have to do this over short distances where the Earth's surface, assuming it's flat, works pretty well. We're going to be working under those assumptions. So this doesn't work if you're launching something over thousands of miles, right? So that requires you to start, treating the Earth as a sphere to get the predictions to be accurate to what we would actually observe. But that's a really nice picture of, you launch something at some speed and it travels upward and then it comes back down. But what's happening is we're not launching only vertically anymore. It's got some downrange velocity. So it's headed off in the x direction, and we're going to have to keep track of velocities in the x as well as velocities in the y direction. That's going to make it two-dimensional. So projectile motion sounds great. It sounds just like what we want to start looking at. So let's start with something easier. I think what they've done here is they've just rolled something off the table. So here's the table, and they're rolling something off of it. Once it leaves the table, it's just gravity that's going to be acting on it. So we're going to neglect air resistance. What happens under the force of gravity, under the influence of gravity exclusively? And what's going to happen here is, look at the velocity in the x direction. Well, the velocity in the x direction is constant. So the velocity in the x direction is staying constant. There is nothing slowing it down in the x direction. So there's no forces acting on it in the x direction. We neglected air resistance. And as a result, Vx just stays constant. Now what that means, and again, each one of these snapshots represents a certain time period. Is that true? Yeah, it is. So if we were to take this object and just drop it, here is how far it's fallen after, 1 second. That's a big table. Here's how far it's fallen after 1/10 of a second, 2/10 of a second, 3/10 of a second, 4/10 of a second, let's say. That's probably more reasonable. So it's falling farther and farther during each time interval. It's accelerating. So the gravitational field is accelerating the object, 9.80 meters per second squared. Now in the x direction, the velocity is staying constant. So projectile motion consists of analyzing the horizontal and vertical motions separately. We can actually treat the x motion and the y motion independently. It actually cleanly separates. So that's kind of fortunate. We don't necessarily have to keep track of x and y combined. In some situations, with air resistance, we have to start thinking about that. There are other situations where, but if we're just under gravitational effect, so we're seeing another picture here. So what we're going to do is we're going to drop a ball here, and here we're going to throw the ball, give it a little bit of a boost, and see how these pictures compare. Now what we can see is that they're dropping they're dropping through the same elevations at the same time periods. So if I look right here at this time, here's the ball over here, here's this one, see how they're dropping right together? Okay, so we're trying to map out that effect. So the y motion is independent. So the rate at which it falls doesn't depend on how much forward motion it has. Now that's true in classical physics. It turns out in relativity it's not quite true, but we're not using relativity. These things are not going anywhere near the speed of light right now. And so at velocities that we're familiar with every day, the y motion and the x motion separates out very readily. And I hope that's what they're telling us in this long and ongoing paragraph. Yes. Okay. So what's happening in the x direction is we keep moving the same amount. I guess the picture before worked better for this. We just keep making the same displacements in the x direction, but the displacements in the y direction are getting bigger and bigger. Okay, here's another good example. What if we launch this from the ground? So if we launch this from the ground, and we're going to look at a lot of problems doing this. So we're going to launch this thing from the ground, and what's going to happen is it's going to have an initial starting angle, and it's going to have an initial velocity. And it turns out that from this, if we neglect air resistance, that knowing the initial velocity and that starting angle is enough to calculate the rest of the trajectory if we assume uniform gravitational fields. Okay, which is a good approximation over not even short distances, let's say, but over some pretty significant distances. This could work pretty well. So, so those are going to be the starting numbers, the Vx naught and the Vy naught components. The Vx naught is going to be maintained all the way through. The Vx is not changing. So all the way through the trajectory from launch until impact, Vx hasn't changed. Nothing to slow it down in the x direction. However, in the y direction, gravity is changing the velocity. So we start off with a good amount of Vy, and it gets smaller and smaller, and then right at the top, Vy is 0. So, and we can use that information to put together some formulas. We'll see how this works. So Vy is going to be 0 right at the top, and then when we come back down, the Vy has reversed. And so the Vy now, we should at impact, if what we learned in chapter 2 is reliable, the velocity at impact is going to be equal but opposite to the velocity, the y velocity at launch. Okay. So that's worth, spending some time and thinking about what is that telling us about projectile motion. Okay, so how are we going to do this? So solving problems involving projectile motion. Okay, that's a little confusing the way that reads. So projectile motion, then, is going to be motion of constant acceleration, but the constant acceleration is only in the y direction. We don't have acceleration in x and y. We only have it in the y. So if we look at the horizontal motion, the acceleration in the x direction is 0, and the Vx is constant, and so there are no acceleration terms going on here. So we only listed 2 of the 3 formulas, because the third one, once you take the acceleration out, well, I guess it still says v is equal to v. Does it work? No, that doesn't really. So we're going to stick with those first 2 formulas. Now in the vertical direction, we do have acceleration, and it's constant. So we can write down our complete set of 3 formulas for constant acceleration, and we have to put all the subscripts in. So over there we put in subscripts for v, v sub x, v sub x naught. Here we're putting in subscripts y, v sub y naught. And then for the acceleration in the y direction is negative g. So what we've done with this problem is we're defining, with these formulas, at least for right now, we're defining upwards as being positive. And so the g, the acceleration, is listed as negative g to remind us that's going to be in a downward direction. So those are the formulas we'll come back to. So solving problems involving projectile motion. Read the problem carefully. I think they said that before, right? Choose the object. Oh, they packed two recommendations into one. Last time that was two separate statements. But now it's read the problem carefully and choose the objects you're going to analyze. I think that sounds like 2 items. Draw a diagram. That was in chapter 2. Choose an origin and a coordinate system. I think that was the same. Decide on the time interval. This is the same in both directions. I guess I'm still not sure what that is suggesting here. And includes only the time the object is moving with constant acceleration g. Yeah, so decide how you're going to handle time in the problem. Here's something to keep track of with projectile motion. So what happens with time is that, if we go back and look at those formulas before, if they tell me something about where the object is in terms of x, how do I find out where it is in terms of y? And the variable that shows up on both sides, both for vertical motion and horizontal motion, is time. So often in a problem, what happens is we'll solve time using one set of formulas, and then once we've solved the time, we'll come back over and use that value for the other set of formulas. We'll see some examples of this. Oh, I've written this down at the bottom. The x and y motion, examine the x and y motions separately. The x and y motions are related, however, by time. So that's important to keep track of. And then again, it's kind of similar. List all of the given values. So whatever they've told us, read that problem carefully. And anything that looks like information, write it down. Doesn't mean you have to use it, but there could be, spurious information given in a problem that they never intend to use, but write it down. Remember that for projectile motion, the Vx is going to be constant, and also remember that Vy is going to be 0 at the highest point. What we want to do is start writing down things that we know about the projectile motion, and then plan out how you're going to proceed. And yeah, you're going to have to use a combination of equations, almost for sure. All right, let's see, how are we doing for time? I think we've got some time left. We could get started here. We have a few minutes to go here. Maybe we'll get started on this, and then we'll come back in the next lecture and finish off chapter 3, starting from here. Let's say that you're going to drive. You're going to drive off a cliff? Really? Okay, so here is a stunt person. They're going to drive their motorcycle at high speed off of this cliff. Now, fortunately for us, they're going to drive horizontally. So the initial velocity that we have, the initial velocity will be only in the x direction. The initial velocity in the y is 0. Now the cliff is 50 meters high. Oh, it's the same cliff we had before. Oh, they're driving the motorcycle off the cliff this time. So, and then the motorcyclist has been, in his contract, he's got to travel 90 meters. If he travels 90 meters, he gets an extra $1 million bonus. Okay, I don't know. Anyway, so we've got this stunt person coming off this cliff at a high enough speed. How fast does the motorcyclist have to drive off the cliff to travel 90 meters before impact? That doesn't sound good. Oh, it is. It's a movie stunt driver, and she is doing what? How fast must change? Oh, you got to land 90 meters. The cameras are all set up, putting a lot of pressure. So ignore air resistance. Boy, that's a good thing that they included that. So here we go. You ready? So projectile motion example. Here, it looks like a bicycle. So I guess I can't draw motorcycles. I can only draw bicycles. So this person's got to ride their bicycle. That's going to make it harder. Really fast, enough that they can travel 90 meters before they impact. Now, for the x direction, there is my formula for constant velocity, x naught plus v naught times t. My formula for the y direction doesn't have any initial velocity. So I'm going to get away with y naught minus 1/2 gt squared. So I kept the other two terms. And then the given information here is h is equal to 50 meters, d is equal to 90 meters, x naught is going to be 0, y naught, I'm going to call that h. So I'm going to say x naught is just 0, I'm just going to let that drop out. But the y naught I'm going to keep around and say that that's actually 50 meters, and then when I land, y is equal to 0. So at the landing. So that would leave me with formulas that look like the distance traveled, so I'm replacing x with d, and v naught times t, and then the h, the distance that I drop, is going to be 1/2 g t squared. So I'm also treating downwards as positive. That'll work. So from this formula, this one's hard to work from right immediately, but this one we can get information right away. And that's because we can get timing information by finding out how much time it takes to drop 50 meters. Now remember, if we just drop the motorcycle 50 meters, it's going to take the same time as if we drive off at this high speed. This formula looks the very same as when we just dropped objects. Okay, so that part of it hasn't really changed. But doing the formulas, I ended up with a time of 3.19 seconds. And then taking that time and plugging it into my distance equation, or not plugging it in rather, but solving for v naught. I have to travel 90 meters in the horizontal direction, and I only have 3.19 seconds to do that. I'm going to have to drive off that cliff at 28 meters per second. That's like 65 miles an hour, 65, 70 miles an hour, something like that. So sure, that's doable. As long as there's no air resistance, we're looking good, but you know, there is going to be air resistance at that speed. I mean, if you're driving a motorcycle at 70 miles an hour, do you notice any air resistance? Yeah, I think so. So we're not going to really be able to make this work, but this is an example of doing projectile motion. So I'm going to stop there for today. We have another day, we'll come back, we'll finish out chapter 3. We'll start with this example with a quick review, and then we'll move on through kind of the rest of the chapter. If you guys have any questions, stop by office hours. Let's get your questions looked at.